So hello again. Before starting, let me explain that this image was taken a few days ago in my city shop run. Saturday morning, we realized that 30-centimeter deep fresh snow arrived and painted the city to a wonderful color. This is a bit unusual. In my childhood, it was much more frequent. About 15 years ago, we had a similar situation. Thank you for joining us. Thank you for coming. This is the third time we organize the winter course. In this year, we are focusing for two topics. Day before yesterday, the topic was the acoustic tomography, and today we are focusing for instrumental root evaluation. This is the second term because this is the identical presentation we had in this morning. The guideline you see for today, it's changed a little bit because recently we realized that focusing on what is the reason that differences are occurred in the static pulling test safety factor and the dynamic safety factor. It is a good reason. So the major of this presentation is focusing on this to answer to this question. Before that, we need to go through a little bit, refresh what is the pulling test, what is the dynamic test, and our goal is maintaining root safety by pulling test and dynamic test. And before that, I just wanted to explain why root testing is important. These are images taken from the Hungarian media, so it's not my images. Shallow root resulted uprooting in Budapest. Very minor root plate. Again, minor root plate, decayed roots. Completely decayed root, impossible how this tree was standing before. Large root plate, but shallow roots. Big tree, a card image. Uprooting happening not only in summertime, and you see it's happening winter as well. As in this image. This is one of my favorite image, large root plate. This tree was standing nearby a tall building as it provided a wind shadow, and it is uprooted. Heavy decay. And now let's see the conifers. Similar situation, shallow roots, small root plate, decayed roots. And the result after storm is uprooting. And thanks for the possibilities. On YouTube, we found a video from New Zealand. And we can see how this pine tree is uprooting. Strong wind. The camera, very sure, soon goes back to the tree. And you see the leaning angle is increasing, sometimes a big step forward to the horizontal. The branches are dancing with the wind, try to equalize in time, but finally the wind was the winning. Yes. And now we can see closer view of the root plate. Unfortunately, a house nearby is damaged, and this person is asking whether is there anyone inside. Hopefully not. Okay, so root condition evaluation is not simple at all. The available instrumental evaluation techniques are the pulling test and the dynamic test. Dynamic test is relatively new. This May we will celebrate the 10th year of anniversary. We presented this technique in city Pisa, Italy. The pulling test has much longer history, developed in Germany, and at least 30 plus years background. As always, in tree investigation, the starting point is the visual evaluation. Let's see what kind of visual indicators are available to detect poor root conditions. Whenever major part of the root is visible, it's definitely a bad sign. When we observe a heavy decay at ground level, very likely it is continuing to the root direction as well. And also in case of spruce, the shape of the tree is changing, is becoming like a skirt. So the tree tries to balance with the situation and increasing the second moment of inertia. This way, for a certain time, quite successful. In this case, visually is evident the decay at ground level. Probably we have decay at the roots, but of course it's not sure. Whenever you see fungi fruiting bodies at ground level, definitely the area is affected. And now pavement reconstruction indicating the lines where the roots were cut before. Here you see perpendicular to the pavement, parallel with the street, and also you can see a little yellow tag on the fence, and it's indicating another line, the yellow tag indicating a gas line. So in these three, very likely the roots are in a very poor condition. Another major indicator is whenever the root plate is moving. In this painting dedicated goes back to 1877. The root plate is already in move, like in this image. This is quite bad sign. Another indicator, whenever nearby earlier uprooting happened, it means that dangerous fungus in the soil are presented, and very likely or probably in the nearby trees are affected as well. Of course, not sure. In this case, we need to apply instrumental test, and let's start with the pulling test. It has longer history. When we are interested for the roots, we are using inclinometer placed at root collar, and the cable are substituting the wind load. This is a static load. Of course, we need to measure the force acting in the row. The basic assumption is the root collar inclination is indicative for the root system inclination. This is true when the root collar is intact and the wood material of the root collar is dominated by matured wood, I mean not juvenile. Juvenile wood has a high flexibility, and that's why we don't recommend to you to test young trees, because in that case you will measure the root inclination plus the deformation of the root collar. So when the diameter is over 30, or even over 40 centimeter, definitely the cross-section is dominated by matured wood. The instruments we are using for pulling tests, we need force meter. We are using two types of force meter. One is the line scale. This is a relatively new one we introduced in our system. Capacity is 30 kilonewton, I mean 3 ton. And the other one, the caliber Rinstrom sensor, has 5 ton capability. And this one has a possibility for connecting by cable and Bluetooth. In case of line scale, the communication mode is low energy Bluetooth. The other important, very important sensor is the inclinometer. this inclinometer sensitivity is pretty high, 0.001 degree, and these two, or when we have more inclinometer, let's say 2, in the case 3 instruments, data is collected by the central unit and transferred to the laptop, Windows-based laptop. It is always an important question where to place the inclinometers, because we are interesting for the root condition. We had to place the inclinometers as close to the ground as possible. And also we need to avoid buttresses, because when we would place the sensor to a buttress, in that case, we would information only for that part of the tree, and the interpretation part of root system is not really developed. So please place the inclinometer as close to the pits, to the tree center as possible. Avoid buttresses. How many inclinometers? 1, 2, or 4? If we are sure that the selected test point, selected location of the inclinometer is moving together with the root system, only one is far enough. But it is we cannot be sure when we have decay at ground level. In that case, we have to select the locations. We need to use more sensors too in our system. But if you are unsure, you can repeat after 15 minutes the pulling test, placing the sensors to other locations and compare the test result. Please wait around 10 to 15 minutes between two pull tests. The evaluation process. The pulling test, we stop pulling at 0.2, 0.25 degree. This is not a major impact on tree. It is just like a stormy condition. We stop and extrapolate the points, extrapolate the curve we got by the measure points. And when the curve, the generalized uprooting curve, goes to infinity, the blue arrow indicating the estimated uprooting force. This is the goal of the pulling test, to know what would be the uprooting force. How these generalized uprooting curve working? I can tell you it's pretty well. Over 2 degree inclination, the applied force is not increasing anymore. As I mentioned, we need to stop at 0.2, 0.25 degree. And it's important that at least 0.05 degree inclination must be achieved for a proper extrapolation. Higher angle is better, but the minimum is 0.05. This is just to show you the generalized uprooting curve. Is a type of tangent function, a little bit modified, but a major part of this function is the tangent. To tell the truth, I don't know where the trees was study maths and learn the tangent function, but working accordingly. The uprooting safety factor, this is an important definition. This is the factor, safety factor, tell us about the safety of the root system. This is the ratio between the uprooting moment divided by the moment created by the wind and the self-weight. When it's leaning, the leaning self-weight itself generating a torque. So the ratio of two torques give us the safety factor. The Stuttgart data table gives us important parameters for the wind load calculation, like aerodynamic drag coefficient, the elastic limit in case of trunk test, and the strength of the material we are using in acoustic tomography safety factor calculation. Our software is controlling the data collection procedure, help us to connect the central unit, and whenever the background is turned to green, indicating we have live communication with the instruments. In this case, elastometer is applied, but today we are not focusing for this. Here you see one result we achieved last week, exactly last week. So this is a 1 week old data set. The blue points are the measure points, and the red curve is the uprooting curve. You see, it's quite interesting. It's not coming from the zero because we are fitting the curve, not the whole data set, but the upper part where whenever we have the higher inclination. In this case, we achieved more than 0.2 degree. For wind load calculation, we need to use, of course, in Europe, the Eurocode. The basic wind velocity in European countries, different location is given by the Eurocode 1991. And you see Italy has four different regions. The Alp is not involved because it's too complicated, so it's a different story. And we have two methods of wind load calculation, and I would like to ask my son György to introduce you the software we are using and the capability of the software we are using for the pulling test and the important part of the pulling test, the wind load calculation.
Okay, thank you. So what I'm going to do is a demonstration based on the software, and it's not going to be slides, it's going to be a live demonstration of the biomechanics calculation based on the Eurocode standard. So now I assume that we have already finished a pulling test, and now we have loaded the data into the viewer. What you see here, for those who haven't used the pulling test so far, the blue points are the measurement points, and the red line is the generalized uprooting curve. After you load your measurement, you are able to add the biomechanics calculation by going to the EN 1991 tab and clicking the biomechanics button. Once you do this, you need to select a photo of the tree. Now this is a horse chestnut, and here we have to specify the crown area, the trunk area, give a horizontal, because sometimes the photo is a bit tilted and there is some leaning, so the software needs to know what is the horizontal, and also a reference length. The buttons on the right give you a hint regarding the order in which you should proceed. So I start by drawing the crown. I click on the crown button and place points along the crown of the tree. You might see that some small branches are outside, but that's not really an issue because those small leaves that are outside are not load bearing. Now I have to be careful because there is another tree behind this one. So as I finish it, I can just click OK, and now I have the full outline of the tree. The second one is the trunk. I need to place 4 points. And then click OK. Third one is the horizontal line. Well, it's difficult to see because the terrain is sloping here, but I believe the picture was taken correctly. So I'm going to try to give just a standard horizontal line here. Right? After this, I need to give a reference. We always recommend to use the whole height of the tree, the total height of the tree as a reference. Do not use small objects, because then you will have higher perspective distortion. So never use a person as a reference, or a car, or a bench. Use something large. For example, the tree itself is is great for this. After placing 2 points for the reference line, I can click OK, and then I have to type in the height of the tree. This is 16 meters. And now I have everything finished with the drawing part. Regarding the information on the right, we have the basic wind velocity. It is also called base wind in the Eurocode standard. This is not the design wind load. This is just the base wind that is defined by the standard for an area. The Eurocode EN 1991 standard is for structural engineers, but it has been adopted by arborists as well. So what you need to do when you're looking for basic wind velocity, you need to consult your national annex, which has different base wind velocities depending on the region in which you are operating. After that, you can select the terrain category. These are also detailed in the standard, and I ask you to refer to the standard. As you can see, you have seashore, lakeside, agriculture, village, city. The difference between these that you are going to have much higher winds on a seashore as you go upwards than in a city or in a village. And I will probably demonstrate this as well. The drag factor is coming from the species. It is essentially a measure of how much wind is caught by the tree itself. Then we have the species density. This is an estimation for the green density. After that, we have the manual tilt angle. It is important to note that a tilt angle is calculated from the image. However, sometimes the tree is tilting towards or away from the camera, and then the tilt is not visible on the screen. In those cases, you need to select the manual tilt angle and change the value accordingly. Another one is the diameter at breast height. Now, this one is calculated from the image as well. However, as you can see, we have a large reference line and a very small trunk, so it might not be very accurate because the trunk that you draw is very small. And giving an accurate outline with such a small region is not always possible. And once you are on the site, it is absolutely possible to measure the diameter and just enter here manually. That also helps us to get better calculations. So you can override this one as well. After you have everything filled in, it is possible to go to the calculations tab. And now for each section of the tree, we have a calculated torque. By sections, I mean these slices as you go upwards in height. When I select a slice, I can see the bottom and the top of the slice. This is going from 0 meters to 5 meters, and also the torque. It is very visible that as I go upwards, the basic wind velocity in the standard has different multipliers depending on the height, and each layer here has a wind velocity. And this wind velocity is used from the top of the layer. So there are several things in the standard that goes towards overestimating the wind load. As I go upwards, you can see that the topmost part is taking most of the wind and most of the torque is coming from there. For every part on the bottom, you can see this calculation. This is a detailed calculation with exact references to the standard. So in essence, the bottom part is telling a story about how we came to the result of the torque. We have a reference. We are using some equation that is referred from the standard. Below that, you can see the exact calculation, then the numbers, the concrete numbers used, and finally the value. For example, now this is how the terrain factor KR is calculated. It is possible to turn off the explanations if you only need the calculations themselves. And this is repeated for every slice. When you click at the top, that is the all parts, then you have the calculations in a single document. It is possible to copy them out with this button and use it in your reports if that's what you want. Right, now we have a final torque. This is 255 kilonewton meters. And when I close this value is propagated. And you can see that we have an M max, that is the maximal torque from the measurement points. And also we have an M wind, that is the torque from the wind, based on the biomechanical estimation. Another use that is very common is since we know that we have a safety factor around 1, sometimes people tend to use the same tool for estimating the effect of a crown reduction. It is very common to reduce the crown from the top, since that's where most of the wind forces, most of the torque is coming from, because as we go higher and higher, the wind speed gets higher as well. And as a demonstration, we had this safety factor around 1, but I will simulate reduced crown area. So what I'm going to do is just change the outline of the crown, and then you will be able to see what happens if we reduce the crown. Just give me a moment. By the way, a right click just removes a point, so afterwards the line is editable. Okay. And now I have a much smaller torque. And once I close this one, you see that the safety factor went up from 1 to 1.5. And this is one common use case for the biomechanics, to test both with the full crown and also a hypothetical reduced crown. And in both cases, you are able to calculate the safety factor. The other tabs here refer to these are the 2 inclinometers, and in the end, those are the 2 elastometers. And as you can see, in all 4, we have a very nice fit. So it's very important that when you see the measured blue points, the red line must always fit very well. The fit is not very important at the bottom, because those are slight inclinations. It's much more important to have a good fit with higher inclinations, because that is going to determine how accurate our predictions are. And with that, I will hand back to Ferenc to continue his presentation. Just give me a second. I need to find a place. All right, thank you.
Thank you, György. It was a good indication that the calculation behind in our software is not a black box. We are using the Eurocode standards, and each step of the calculation we have clear references. Now it is quite an interesting question how the generalized uprooting curve working. Whenever we do not stop increasing the pulling force, achieving the 0.2 degree limit, we can go up to the point the tree is uprooted. This graph shows you 10 trees story when we stopped at 0.2 degree and used our software and predicted the uprooting force. This is the horizontal axis. The vertical one, you can see the real uprooting force, what we measured, and we compared it. All the points, all the 10 trees, we can state that the real uprooting force is higher than the predicted. So the system is conservative. Roughly 10 to 20% is the deviation, except one we see much higher deviation, but it's only one case among of 10. So for this reason, the pulling test safety factor is lower than the real one. The other reason that the pulling test providing a conservative lower safety factor than the real one is the calculation do not take into account the effect of the surrounding buildings and surrounding trees. So we assume that the total wind attacked on the tree and no any shelter nearby. For these two reasons, I mean the uprooting function, the generalized uprooting curve working mode and neglecting the surroundings is definitely we will get a lower and conservative safety factor. Pulling test has number of limitations, sometimes not easy to find an anchor point to fix our rope. Whenever no other trees nearby, I mean within 30, 50 meters, in that case we need to use heavy lorry. The pulling test is a static load, but the wind is a dynamic one. So we little bit modified the pulling test. Instead of ropes and winch, we are using the anemometer placed on 10-meter height using the anemometer pole. And this is a more realistic test conditions and sensitive to the surroundings. So it looks many benefits, but also it's can be a drawback you will see later. The DynaTree setup one anemometer, and within 1 or 2 kilometer radius, we can test trees, as many incrometer we have. And the principle of the dynamic route evaluation is, well, mechanical stress is necessary, same as in case of pulling test. In this case, wind creates the mechanical stress. The anemometer placed at 10-meter height on a location when the wind speed is undisturbed, it's open field. The incrometers placed at the root collar, close to the tree center, to the pits. We need to avoid buttresses. This is identical like in case of pulling test, but we need wind. This technique is not working when wind is not blowing. The software gives you safety factor whenever the wind gust velocity goes above 25 km per hour with warning. We recommend wind gust velocity above 35 km per hour. And also the evaluation based on statistical evaluation. So the minimum data collection time is 1 hour as a minimum, but the recommended is 3 hours. Longer is better. You know, we have more data, the statistical evaluation is more valid. The statistical window width, you will see a little bit later. In 5 minutes interval, we handling all the data together, and it is 5 minutes. Whenever the tree and anemometer distance is more than 1 kilometer, instead of 5 minutes, we recommend to use 10 minutes. The dynamic test is sensitive for the surrounding building and trees. Itself is a good message. We are closer to the reality comparing to the pulling test. The result is affected by the wind direction as well. If the tree is standing in a wind shadow, the measured safety factor will be unrealistically high. I mean, in a wind shadow, low movement, high safety factor. Depending on the wind direction, the same tree can receive a wind from an unsheltered direction. In this case, it may show remarkable lower safety factor, closer to the reality, of course. The troubled root structures may have some other resulting other troubles, but let me jump over this phase. Here you see the inclinometer. You see exactly the identical inclinometer in case of pulling test. High resolution, 1 millidegree resolution, sampling rate 10 Hertz, data saved on SD card. Very large amount of data can save. I mean, a whole year can place on the SD card. And we have two sensors, one in X and other is in Y direction. The anemometer, we are working with two anemometers, ball type and ultrasonic type. The ball type is manufactured in Italy. The ultrasonic type is manufactured in France. A portable anemometer pole in closed position, length is a little bit over 2 meters. When we erect it, it goes up to 10 meters, where we need to measure the reference wind speed. This graph is indicating what means open field. We have turbulences made by object 20 times the height of the object, so it's quite severe condition. Because the sensors, the incrometer, and when we are testing the tree trunk, in that case, the elastometers are identical for the pulling test and for the dynamic test. And for this reason, no, not necessary to purchase more sensors. The difference is, one case we are using anemometer, and other case we are using force meter. Here you see the graph is indicating what I already mentioned. The red marked area is instruments need for the dynamic test, and the blue marked area is need for the pulling test. The first step of the evaluation, we need to set the statistical window length. This is the preset value is 5 seconds. This is what we recommend. And also we need to select a region of our test where the wind direction was uniform. In this graph, upper part you see the wind speed, middle section indicates the wind direction, and the bottom you see the inclination. The highlighted area here is the area which is taken into consideration in the evaluation. So we need to select the region. We need to separate this section with the section to the right, because the wind direction is different. I already mentioned the statistical window width. This is what I mean. This is normally 5 minutes, the time in between the two red lines. And this is important parameter in the evaluation. Why the statistical approach is important? It is just a similarity how the fluid is mixing with the high velocity and no standing fluid. The mixture is quite complex. Turbulences here are like around the trees. But when we take the time average, this complicated feature is becoming very smooth. So it is just similarities indicating that in case of this complex situation, statistical evaluation give us the possibilities to get good results. Just again, going back to the averaging time window width, when it is 1 second, the correlation between the wind pressure and the correlation between the wind speed and the inclination is very low. When we open the window at 5 minutes, it gets back quite a pretty high values. Here you see when we place the anemometer close to the tree, it was a tree standing really alone. There was no any object nearby, and the anemometer placed the location where the wind attacked first the anemometer pole, then arrived to the tree. We got extremely high, over 0.9 correlation coefficient. Whenever the distance between the anemometer and the tree we are testing is 2.5 kilometers, still we got safety factor above 0.8. Whenever it was an accidentally situation, the one anemometer relatively close to the tree damaged, and we had to go select another anemometer more than 5 kilometers, and we still got acceptable correlation. especially at higher averaging time window region. What does it mean? Whenever a weather front hit the area, we can apply a little bit higher differences between tree and anemometer, but local wind effect like tornado, this one is not working at all. The safety factor determination. This is identical like pulling test. We need to calculate the torque between the uprooting torque or the critical torque divided by the torque made by the wind and the self-weight. In both quantity, both torque, we need to use the crown area, the crown center height, the aerodynamic drag coefficient. And it means that these parameters are neglected. This one has relatively high safety, high error margin. For this reason, this is really good news. So this is the beauty of the dynamic test. Here you see a real data set. You see the wind pressure and horizontal. This is coming from the wind speed. The wind pressure itself is equals density divided by 2 and multiplied by the velocity on the second. So the one factor is not taken into consideration, how frequently the test area, the tree area, is visited. Whenever this is highly frequented place, we recommend to use the safety factor instead of 1.5. We recommend to use 2 as a minimum. In other case, the limits are similar, like in pulling test, above 1.5 low risk, between 1 and 1.5 medium, and below 1 is high risk. So again, how we evaluate the inclinometers. Here you see number of points. Some of them is open, some of them is full. You see the full dots above the dashed line. It means that we separate the measure points and we take into consideration only those are showing higher inclination, and in this way it is a type of pessimization of the method, but we believe in this way we are closer to the real safety factor. We always give a statement around the final result that the safety factor can be highly dependent on the wind direction and the surrounding object. We got a very nice data set from Tim Moya Associates 4 years ago. Mr. Jim Chambers measured a tree several times with really high wind speed, was close to 120 kilometers per hour, and at a different wind directions. The little red arrows are indicating the wind direction. The red cross is indicating the location of the tree, and the yellow cross indicating the location of the anemometer. Perfect anemometer location. But when the wind arrived from south, 208-degree direction, the safety factor was pretty high, almost 4. Yes, because the wind first attacked the building and only part of the wind forces arrived to the tree. But when other wind direction, the safety factor went down just below 1. So remarkable big change may occur. The same situation in Austria, 2 wind direction, not a big change in direction. We've seen earlier this data set. We've seen the data set on the left, and the left part selected for the evaluation. Safety factor is 0.8. When we selected another wind direction, shows on the right. In that case, the safety factor goes above 1.6. Very big differences, yes, because the surrounding object is affecting the wind very much. So this is really important to keep in mind that the pulling test and the dynamic test has two different principles. They are measuring different things. Of course, measuring the inclination, this is identical, but once we measure force, other cases we measure wind speed. The dynamic test measures undisturbed wind at the anemometer and compare the reaction of the tree to this wind. It has a large emphasis on the effect of the surroundings, and this is really good news. It means that we are able to get perfect result whenever we have a chance to measure the tree in all kind of wind direction. Theoretically is possible, but in practice, I guess it's not really. That's why we need to really set the anemometer perfectly to north to have the correct result in correct wind direction information, and taking into consideration whether the tree was standing in a relatively open position for the wind or in a wind shelter. The contrast is the pulling test, when we assume that the tree is a solitary tree and receiving the full wind load. So that's why these two safety factors cannot be identical. The different methodologies give us different numbers. This is important to understand the underlying principles and the reasons of the differences. Let's see a theoretical situation. I got a numerical analysis from Franziska Hunger from Fraunhofer Charles Research Center. This is a housing estate, tall buildings, and calculated how the wind react around the buildings in case of western and northern wind. The arriving wind speed is 6 meters per second, and I selected a point where the contrast between the two directions is the highest, probably the black point. Let's assume that the tree is standing over there. Let's assume that the safety factor, the real safety factor, is 1.7. Whenever we calculate the pulling test, we need to calculate the full wind, the 6 meters per second, so the safety factor, instead of 1.7, becoming 0.9. The dynamic safety factor in case of west wind goes up to 4.5 because it was almost in a wind shadow. So we need to take into account this information, and generally pulling tests give us a lower, and the DynaRoot dynamic test safety factor is a higher safety factor than the real one. It is good, the theory itself, but the practice is most important for us. How it is working. Luckily, Christoph Németh, the CEO of the Dendro Complex company, performed a test in Budapest, Pozsonyi Street. The yellow line is indicating the street relatively close to River Danube, and this is a narrow street. And thanks, Christoph, for the data. Here you see the street, the Pozsony Street. In the middle, you see an electrical line. It made difficulties for performing the test. They had to close the traffic, switching off the electricity. They need to ask the car users not to park that area. Those who are forgotten to do, they need to mechanically remove the cars. So it was not an easy task, but they performed and did 116 tests, and among of them 38 was tested by DynaTree as well. Only 2 trees were removed because the poor safety result, and I already mentioned the trolleybus and electrical line difficulties. Another difficulties was the elevated soil, so they had to dig 20-40 centimeter deep hole for accommodating the sensors, because the goal was to place the sensor at the original root color. And unfortunately, the space for the trees and the roots are very limited. These are the results. Normally, we are speaking for safety factor for roofs in both cases, but the numbers are different. The reasons, I guess, explained earlier, but the data, what the data says, almost one half of the data is in the range plus minus 15%, or plus minus 50%. It means that the error of the pooling test is roughly in these regions. So that's why whenever we got deviation between the two safety factors is in the range or less than plus minus 50%. In this case, it is overlapping well. Only 4 points we found that the pooling test safety factor was highest, and to tell the truth, at the moment I don't know a clear explanation why this 4 point is happening. But on the right side of the orange dots, you can see another 17 trees where the dynamic safety factor is much higher. Yes, because those trees were standing in a wind shadow. Christoph explained me that during the test, they not only performed the data collection, but also observed how the trees are moving. And they found trees that trees was not moving, almost not moving at all. And the other trees on the same street was moving a lot. So it is really complicated how the wind is acting around tall buildings, narrow streets. Okay, so let's go to another field. Last spring we had a nice test using pooling test and how the anchorage height is affecting the result. Based on the SEG German standard, the recommendation is the anchorage height should be in between 1/2 and 2/3 of the tree height, roughly in the tree crown center. It's marked by the orange arrow. The effect of the anchorage height is tested between 4 meters up to 16. Only the 2 dots on the right is fulfill the German standard recommendation. But quite interesting, below 6 meters, we got almost uniform safety factor. This may indicate that we can anchorage a lower point, but keep in mind it's only one tree, one test result. Let me mention that whenever you are testing the trunk and using elastometer, it is not a good solution. I mean, anchorage height lower than the recommendation of the SEG standard. In that case, this really we need to follow. And also we tested the effect of the rope angle. The angle was tested between 19 to 45 degrees. And again, we got very similar safety factor, quite interesting. We first did the anchorage height test, this one. The safety factor was around 1.8. We waited at least 15 minutes between tests. And then after lunch, we continued with the rope angle test. Anchorage height was identical, a same tree. And in this case, the safety factor was a little bit lower. Probably the tree root system was getting tired. These data sets indicating never use 45-degree rope angle. It's a bad idea. Why is bad? Because the wind is horizontal, so we would need to use as low angle as possible. Next day, we got a tree from the FAKOPP company. This company is taking care of all the trees in Budapest. An Acer negundo tree. It's partly died, as you see the crown. And first, we measure the safety factor for 4 direction, north, east, south, and west direction, and almost the uniform safety factor got. It is really a pretty good, pretty nice result. and good selection for testing the root damage study. We made root damage. First, we made a root mapping, and we selected the area shows on the right where we have more roots. The location of the roots is marked by lime powder, and the excavator machine is decided to work perpendicular to the direction where we found the major roots. 3 line was excavated. The first trench was made under the edge of the crown, a little bit more than 4 meters from the tree center, and only minor roots were cut. And we repeated the pulling test for direction, and we tested what is the effect. I will show data later. The next trench was made 2 meters from the tree. Depth of the trench was 80 centimeter. And here you see the instrument we are using for the pulling test, the force meter, the central unit, the laptop. This battery powering all the units and the inclinometers. I mean, the force meter is powered by its own battery. And parallel with this test, a root wound treatment demonstration was made. And this is quite a rare situation where people are able to observe how this wound treatment is happening. Yeah, so the last trench was close to the tree, half a meter from the tree center. And on the right, you see Tibor Horváth back, and he is wearing a t-shirt indicating a text. I'm arborist and I do not like to chat, because he realized that many people are interested in what an arborist is doing, and when he's chatting too much, the work is slowing down. Here you see the result. This is really the interesting result what we got. On the table you see the numbers, the initial state safety factor, and the trench 4 meter, 2 meter, half a meter, and finally the last trench buried as well. The graph below is indicating the relative safety factor drop. I mean, how many percentage the safety factor is reduced as a result of digging. You see the major impact was found when the pulling direction was to the north. In this case, we would pull the missing roots in tangent, and these are more important. 35% safety factor drop observed when we place the trench just half a meter from the tree center. It was the closest position for the excavator. There was always no influence. It only at the highest, the more severe attacked. In east case, when we pull to east, we pull parallel. So all the important roots in this case are intact or almost intact. That's why the impact is minor. South direction, the second perpendicular, almost perpendicular direction to the trench line is indicating again a relatively high, but a little bit less than the north direction, and west is in between these two. Okay, so the conclusion is whenever we have root cut and perpendicular to the trench line, the safety factor is always lower than parallel with it. At the end, let me show you a new elastometer we developed. This is not really linked to the top topics, but it's used in the pulling test as well, and also in the dynamic test. You see the resolution is 0.1 micrometer. It's pretty high, and when I compare with the old and the new elastometers, the sensor component outside looks identical, but in the new version, the electronics is pushed inside the steel housing. So it is less cable and easier operation. And also for practical application point of view is the power consumption is reduced very much. So the whenever the previous one was 100%, now it is 30% of the power consumption. So your battery lasts 3 times longer. And now, thank you for your attention.